Hello, we are Team Hemlock.
Hemlock?
Hemlock?
Yeah.
My name is Keegan Knutson.
I'm Christian Parker.
I'm John Willis.
I'm Matt Phillips.
And I'm Dentrell Ford. And the instructor's name is Raul Vargas.
Raul Vargas.
Vargas.
And this is the month of February. Our class is Monday, Wednesday, Friday at 9 a.m.
Physics.
Yeah.
Physics. Today we are going to be showing you the inverse square law and how it relates to sound.
And particularly, how it relates to our industry.
The inverse square law was first proposed by a Sir Isaac Newton in July 6, 1687. The equation of the inverse square law is intensity equals 1 over the distance squared, or raised to a power of 2. The function states intensity is determined by how close or far an object is from the source. In addition, every doubling of the distance results in a loss of 6 decibels, while a halving results in an increase of 6 decibels.
For the purposes of our experiment, we had to convert the amount of acoustic energy produced into decibels first. So we found by plugging in values to the logarithmic equation that every time we double the intensity, we will go up approximately 3 decibels. However, we want to go up 6 decibels, so we must increase the intensity by 4 times. When we plug this into the inverse square law, we find that in fact it does cut the distance in half when we increase the intensity by 4 times.
Hemlock!
There are several factors that can affect the inverse square law. The inverse square law is always in effect. However, many factors, such as the environment, can cause a big difference. Rooms that are very reverberant can cause unwanted echoes. Standing waves can also affect this law. And also, the ambient noise in many different environments can cause misreadings.
I want to be a billionaire.
This is our first trial. We're doing inside McDonald's. Our first distance is 2 feet away from the source. So here we go.
Alright, now we are at 4 feet. We just doubled the distance from 2 feet.
Take 3 and we double the distance from 4 to 8. Let's see.
This is original.
This is take 4 from 16.
Alright, so we're at my house, and now we're doing another test with an amp. And Keegan's playing guitar. And we're starting at 2 feet and 4 feet, and then we're going to 8 feet. So here we go.
It's a lot of feet. Alright, now we are at 4 feet, and I'm going to be playing the same chord progression at the same volume.
Alright, so we doubled the last distance, so now we are 8 feet further away. Here's our readings now. Now we're doing our second experiment, and we are doing a white noise from the same distances. Here we go.
2 feet away. Ghost.
So now we doubled the distance, and here we're at 4 feet.
Scratch and win.
Hemlock.
Take 3. We doubled distance from 4 feet to 8 feet, and here's our readings.
Oh, readings.
The inverse square law is incredibly useful in the recording industry. By using the inverse square law, you can figure out exactly where you need to place a microphone to record different instruments or sounds without getting any distortion or unwanted effects.
Hemlock!
In conclusion, we have found that the inverse square law holds true to its formula. For every doubling of the intensity, it raises the sound intensity by 3 decibels. For every doubling of the distance from the sound source, results in a loss of 6 decibels, which is 25% of its initial intensity. During our test, the clicking of the snapshot button on the SPL meter threw off our reading slightly, since the SPL meter picked up the clicking on the computer. However, after analyzing all the results, all the experiments showed a drop of between 5 to 6 decibels. Here are our results. Due to different factors that affected our experiments, there's always room for error. Although, this project proves that the inverse square law is much in effect in everyday life. This law is very important to the recording arts industry to guarantee desired intensity levels and to cut back on unwanted effects.
Hemlock!